My name is Hunter Costello, and I'll be going over Lab 1 for EE120. We'll be looking to a half adder, 4-bit incrementer, full adder, and a 4-bit full adder. On the screen right now is the half adder, in which A and B are a binary input each, and I like to imagine that the output is a 2-bit binary number, carry being the left binary number, and sum being the right bit. And we see when one of the inputs is 1, that the output is going to be equal to 1 or 0, 1, as I imagine it. And when both are true, the output's going to be 1, 0, the binary representation of 2. And the waveform shows that what I say is substantiated. When B or A is equal to 1, the representation is 0, 1, and when they're both 1, the representation is 1, 0. And next we'll be looking into the incrementer, the 4-bit incrementer. And with this design, what it aims to do is increment A by 1 and get it to output Y. So if we make A any random number and click the incrementer, it's going to increment it by 1, unless we make A F, in which case it's going to cause an integer overflow, resulting in Y reverting back to 0, because it can't represent a digit that high. And I'll be bringing up the waveform for this one. And we see A plus the incrementer is going to be equal to Y. A can be anywhere from 0 to F, or 0 to 15 if we're talking about decimal numbers. Incrementer can only be 0 or 1. So A plus 0 or 1 is going to get Y. And we see through A being 0 through F and incrementer being 1, it adds 1 every time. And in that case of A being F, it reverts to 0, causing overflow. And when incrementer is 0, it's just going to be equal to A. The next design we'll be looking at is the full adder. This is going to represent more of the full adder, the 4-bit full adder, in the case where Cin is going to come from the bit placed before it if it carries over a 1. And this is also like a 2-bit binary input, like the half adder, in which we see binary addition. 1 plus 1 is going to equal 2, and 1 plus 1 plus 1 is equal to 3, in which the sum stays in the binary digit place where this full adder is, and C out will be carried to the next place. And I'll bring up the waveform for this one next. And we see that the waveform represents this. When only one of them is 1, it's going to show that the output is going to be 1. When 2 of them are 1, it's going to represent 2. And when all are true, it's going to represent a 3. And that's going to carry us over to our final design, the 4-bit adder, in which we take 2 numbers, add them together, and we have a incrementer if we choose to increase it by 1. So to show it, let's do 2 plus A. And we see that A plus 2 is going to be equal to C, and if we choose the incrementer, it's going to increment it by 1. But let's say we wanted to do 4. That's going to result in F, and if we go 1 higher, it's going to result in integer overflow. And I'll bring up the waveform with my own custom test to show how this works. In this waveform, these numbers here represent all the tests I've written in the 4-bit adder stim.txt file. These all tests right here have been applied to the waveform and show if my equations were true or not. So we see that in some cases, as in F plus F, or C plus C, or A plus B, that they go too high in the binary range and revert back to 0 or a number that's lower than they're supposed to be. And we see that depending on which case, so if it overflows, it's going to result in the binary representation of 2. If there's a carry out, it's going to represent in 1, but if there's an overflow and a carry out, it's going to represent in 3. And with that, that is the end of my presentation on Lab 1, how we use a half adder, 4-bit incrementer, full adder, and a 4-bit full adder.